Hello everyone, my name is Ma Ziyi. We come from Wuhan University, one of the most beautiful universities in China. Today, we talk about the feature selection in software fault prediction. This is a joint work with Yu Xiao. First of all, let's talk about the motivation of our work. Software defect prediction is one of the most important software quality assurance techniques. It aims to detect the defect provenance of new software modules, but they are usually confined to predicting a given software module being faulty or non-faulty by means of some binary classification techniques. However, predicting the defect provenance of a given software module doesn't provide enough logistics to software testing in practice, so it may result in a waste of limited maintenance resource. Thus, predicting the number of faults in software modules can be more helpful, instead of predicting the modules being faulty or non-faulty. But irrelevant and redundant module features may undermine the prediction effect. So, our purpose is to select the more effective feature subset for the number of faults prediction. Then, we talk about the related work. Defect prediction. Many researchers have proposed various models for predicting the module being faulty or non-faulty. Support vector machine, neural networks, decision trees, and Bayesian methods paved the way for classification-based methods in the field of defect prediction. These methods use the software metrics to properly predict whether a module is defect-prone or not. A number of prior studies have investigated regression models on predicting the number of software faults. However, the prediction performance of these models gets worse when the defect datasets contain irrelevant and redundant features. Feature selection in defect prediction. A number of prior studies have investigated feature selection methods on predicting the module being faulty or non-faulty. Chen proposed a two-stage data preprocessing framework (TC), which combines feature selection and instance reduction. Liu proposed a Liu feature selection framework (Fscr) to conduct feature clustering and feature ranking. Then we talk about our approach, Fscr. In this section, we present our Fscr method for the number of faults prediction. Assumes that the dataset has 10 original features, represented by hollow circle in figure. First, we compute the correlation between every two features. Then, we partition original n features into k clusters using spectral clustering algorithm. In the first stage, these 10 features are partitioned into 3 clusters by using the spectral clustering algorithm. Next, we use the relevance measure to compute the relevance between every feature and the number of the software faults. Then, we rank the features in every cluster in descending order according to the relevance. At the last, we add the top features of every cluster into the feature subset. In the second stage, we rank all features in every cluster based on the relevance between each feature with respect to the number of software faults, and select the top P features from each cluster. Therefore, the final feature subset contains 1, 6, 7, and 8. Then we talk about the details of our experiment. In this experiment, we employ 6 available and commonly used software project datasets with their 22 releases which can be obtained from Promise. In the experiment, we employ root mean square error (RMSE) to measure the performance. In addition, considering the imbalanced characteristic of software defect datasets, we also employ 3 commonly used performance measures that evaluate classification models, including PD, PF, and G measure. These performance measures are defined in Table 2 and summarized as follows. Our experiment aims to answer 2 research questions. Question 1. Does our proposed Fscr method perform better than state-of-the-art feature selection methods in terms of predicting the modules being faulty or non-faulty? In the experiment, we compare our method with 6 classical feature selection methods in defect prediction: 4, CS, GR, S2N, IG, FECAR, and we employ 3 regression models in defect prediction: Bayesian rigid regression (BRR), gradient boosting regression (GBR), and linear regression (LR). As is shown in the Table 3, the values shows that on 3 regression models, Fscr outperforms others on over half of projects in terms of all the 3 measures. Figure 2 shows the book plots of G-measure values with 6 methods for 3 regression models on 6 projects. According to the experiment results, we conclude that Fscr can perform better than state-of-the-art feature selection methods in terms of predicting the modules being faulty or non-faulty. Question 2. Does our proposed Fscr approach perform better than state-of-the-art feature selection methods in terms of the accuracy of predicting the number of the software faults? Tables 4, 5, and 6 present the detailed RMSE values of each project on 3 regression models. From these tables, we can observe that Fscr performs better average RMSE value than all the other methods. In addition, HGG is employed to demonstrate the effect size. The effect size of HGG values are greater than 1 on most projects, which can be interpreted as a nudge improvement. Answer for question 2. According to the experimental results in tables 4 to 6, we conclude that Fscr can perform better than state-of-the-art feature selection methods in terms of the number of false predictions. At the last, we talk about the conclusion. In this paper, we propose a novel feature selection method for the number of false prediction. The method involves the following two stages. In the first stage, we employ a feature spectral clustering method to cluster the original features. In the second stage, we select the highly relevant features from each cluster. Experiments on 6 projects datasets indicate that the proposed method, Fscr, can perform competitive results for the number of false predictions. The future work. In the future, we will further investigate the impact of the parameter settings, such as the number of clusters and the number of features selected from each cluster. In addition, we would like to validate the generalization ability of our method on more datasets. Oh, that's all. Thank you.